now?
Yes.
Your whole screen, yes.
Okay, do you see this blue screen that says about the school?
See your desktop, not the
We see your
Alright.
desktop.
Okay. This is actually the first time I'm trying YouTube live streaming. So thank you for your patience. How about now?
Yes, this is great.
Okay,
Yeah,
great. And you can see me. You can see
Yes.
both the presentation and me. Okay, great.
Yes.
I play second fiddle to none, even the presentation. All right. So, all right. So on the third bullet point, I was just talking about how our bootcamp is the only one that offers both Python and R. Over the course of the bootcamp, you will be asked to complete 4 industry projects that demonstrate comprehension of the modules and the concepts, including the capstone project that will tie everything together. And depending on the cohort, there also is an opportunity for you to work on project pitches from our industry partners. So that is a great opportunity for you to increase your visibility in the data science community. We have very strong job placement support in the form of mentors. There are one-on-one mentoring sessions where, in addition to homework and project help, you also have career help, in that a lot of our mentors are alumni who graduated from the academy, and you can get their take on how they landed a job, the work culture at a particular company that you're interested in working at, or anything that might be relevant to your job search. In addition to that, our career services support offers mock interviews, resume reviews. We keep close contact with our alumni, and we invite them back to alumni networking events, alumni workshops, coding workshops to keep their skills sharp. You are added to our job portal upon graduation so that you will be in a select list of people our industry partners have visible, who know that you graduated from the bootcamp and who have survived the rigors of the bootcamp. And you have lifetime access to this. So after you land a job, if you want to, after a few years at that job, want to come back and are curious in another sector or industry, you can toggle your visibility in this job portal back to on and continue searching in another sector with your added experience. So we want to keep our network growing, and we value the our network so that you will find a lot of added value having graduated from the New York Data Science Academy long after graduation. We have 2,000 alumni working across the globe, and our diversity is reflected in our faculty, our student body, and our industry partners with division offices all over the world. And we're also proud to say that we have been consistently highly ranked in both Switch Up and Course Report.
I'm going to step into this meeting.
There are 2 delivery formats for our bootcamp. One is in-person / live streaming. And that one would be, you have about a 2 to 3 hour lecture in the morning, after which you break for lunch for about an hour and 15 minutes. And then you return to afternoon lecture, where that is also 2 to 3 hours. The rest of the afternoon you have available to ask instructors questions, collaborate with your peers on projects and homework. This one is 12 weeks, and the next cohort begins July 6th. If you missed this window, you have another opportunity coming up in September 27th. You may apply for that one. The second option is the interactive distance learning, which is our online option where lectures are pre-recorded. And aside from that, the level of interactivity with instructors is the same. The amount of career support is the same. The content is identical. It just provides a bit more flexibility in terms of timing of the lectures. You can watch them after work or on a schedule that better suits you. And you get, for the full-time program, an extra 4 weeks to complete your work. So instead of the 12 weeks, you get for live learning, you get 16 weeks for full-time. Or if you're a full-time student or full-time professional, you get 24 weeks to complete it. There is also the data analytics bootcamp that I mentioned earlier. This one is also interactive distance learning, part-time, 12 weeks. So you have several options to choose from. And the start dates for these are July 6th and August 16th for the interactive distance learning pre-recorded lecture option, and July 6th for data analytics. If what I say interests you, feel free to go ahead and submit an application. The application process is very simple and quick. You submit an application, you then schedule an interview, after which someone from the admissions team, either myself or Noah Escobar, will interview you to assess your goals for the program, what interests you in data science, and your fit for our program. If we find you a good fit, we'll then send you a technical assessment that you'll complete within 48 hours. It will be forwarded to one of our data science instructors who will grade it and provide feedback as far as the areas suggested for review before the beginning of the bootcamp. If you apply for the August cohort, we are running a 10% discount. You'll be saving almost $2,000 on your tuition if you decide to apply for our August interactive distance learning cohort. So that's something to consider. That's quite a bit of cash you would be saving. If you have any more questions, please feel free to email me at this email address, and I'll also provide you my personal email. I'll drop that in the chat, and let me figure this out. Stop share. And I will turn the, if there aren't any questions, are there any questions? I'm sorry, I wasn't paying attention to the chat box. Let's see. I don't think so. If you have any questions for me specifically, go ahead and email me, and I'll turn the presentation over to Carlos now.
Hi, can you hear me?
I can hear you.
Great. Sophia, I believe you may have shared your email just with myself. So on the Zoom, you may want to share with all the participants, because I think it went just to me, your email.
Oh.
Yeah.
Zoom is so clunky. I'm not taking any fault for this. I'm blaming Zoom.
That's all right.
Okay.
Okay. Let's try sharing again with everyone.
Okay.
Great. So everyone has Sophia's email now. And as I start, could you actually just go and mute people? As the host, you are able to mute everyone so we don't have background noise. All right. Thank you, everyone, for joining today. I'll start sharing my screen, and we'll start with today's webinar. All right. Can you see my screen now? You can give me a thumbs up in your camera or in the Zoom. Yeah, on the chat. That's great. Thank you. Great. All right, I still hear some background noise, so if you could mute yourself, otherwise Sophia will go around and mute your mic so that everyone has is muted for today. The interaction today, I just noticed we have quite a lot of people here. Normally during our classes, we have small groups of people and everyone is with the mic on and everyone talks and it's a conversation. However, today we have a lot of people. It's impossible for everyone on with the open mic, because as you saw, some people have background noise and so on. So I encourage you to use the chat as the a medium of communication. And I'll be asking some questions, and I'll encourage you to try to answer those questions, at least in your head, to make this more interactive. And you can also share your answers on the chat. And then at the end, we'll have a proper Q&A session. So you can also hold on your questions for the end. All right. So my name is Carlos Afonso. I am a data science instructor at the New York City Data Science Academy. And it's my pleasure to introduce you to this topic today, A/B testing for data science. And we'll be using some coding in Python and R. So this is actually an introductory webinar so that you learn some important statistical topics that are involved in A/B testing, and also so you get an idea of how it is like to code in Python and R. Here's the outline for today, and actually I'm going to increase this so you can see it bigger. Again, if you could mute yourself, or Sophia could mute you, that would be great. So don't have the background noise, please. Okay.
I'm having trouble administratively muting people. I mute them and then they come back on. So they would have to do them themselves. I tried to do that earlier with the guy blaring his music, and it just kept blaring.
Okay, so if someone keeps being too noisy,
should I remove them like I did?
It will be removed from the Zoom. I'm sorry.
Did you all hear that?
Yeah, if you are too disruptive, we'll have to remove you. I'm sorry about that. So that for the benefit of everyone else. Okay. All right. So the outline for today, we're going to talk about A/B testing, an introduction to A/B testing, what it is, why do we use A/B testing. We'll talk about some general examples and some specific examples, and then we'll explain how A/B testings are done. And in particular, we'll go in detail about the hypothesis testing part and what is the concepts involved in hypothesis testing, such as the p-value, which is a concept that is often difficult to understand and misunderstood. So we'll have a good explanation of what the p-value is. We'll actually be using what's called the permutation test to do the hypothesis testing part of A/B testing. So that's another thing that you'll be learning today, what's a permutation test. And I'll explain what it is and why we use it and how it's done. Again, we'll explain step by step how it's done. And after that, after kind of the introduction and explaining the general concepts, where we'll use some visualizations to explain those concepts, we'll have a coding session where we'll code these concepts from scratch, both in R and Python. And at the end, if you have extra time, I'll provide you with a more general solution, and I'll even show you a Shiny app where you can manipulate all of these things. And of course, at the end, we'll have a Q&A session. Okay, so the learning objectives for today are separated in two important parts, statistics and coding. In terms of statistics, you'll learn what are A/B tests, what's hypothesis testing, what are p-values and permutation tests, and other concepts related to hypothesis testing. Regarding coding, you learn about variables, loops, and functions. Okay. I will. So apparently you can see some gray on the bottom. Is that, okay, it's better now. Okay, so it's good. All right, so let's start. You are here because you're interested in data science and maybe particularly interested in A/B testing. So I would ask you, what's an A/B test? You can try to answer that in your head, or you can share the solution or your answer on the chat, so you can interact with everyone else. Okay. So what's an A/B test? Have you used A/B test? Have you read or started learning about A/B tests? What do you think is an A/B test? I'll give you a moment to think about that and to provide an answer. Okay. So let's see if anyone shared. Test between two alternative paths to determine which accomplishes the goal better. That's a great answer. Thank you, George, for sharing. Yes, in simple terms, an A/B test is an experiment to compare two competing options, and we call them A and B. Those options could be, for example, 2 different treatments in a medical context, 2 different designs in terms of, say, 2 different adverts or 2 different versions of the same advert to see which one would be better, 2 different web designs, 2 different products or 2 different versions of the same product, having the same product, trying to sell at the same price to see what in the end gives you better profit, and so on. So it could be any 2 different options for a problem that you are trying to improve. Okay. And why do we use an A/B test? Well, we want to determine if those 2 options, those 2 competing options, A and B, are different. And different how? Different in a statistical sense. And that's where we'll need to use hypothesis testing. And today we'll be using a permutation test to do the hypothesis testing part. Normally, we actually don't want to just know if A and B are different. Normally, we want to know which of them is better, if one of them is better than the other. Why? Because you are trying to kind of solve a problem, and you are trying to find which of these 2 options is better for solving the problem. Okay. Again, the better depends on what type of question or type of problem are you trying to solve. And it's the better in the sense that it will be the better one at solving that question or achieving the goal at hand. For example, what of the 2 options would be better, say, for increasing the number of customers for your company or for increasing the profit of your company? Those are 2 different goals that may require different options to achieve them. So some general examples, for example, we can have 2 different soil treatments to try to understand which of them may promote better seed germination. The statistical concepts have a historical root in agriculture, and this still today it's still used a lot in improving crops and so on in agriculture. More modern examples, 2 web headlines, say, of a news article or of a blog post to understand which of them generates more clicks, or 2 web designs of web pages, landing pages, to understand which of them may lead to more conversions. Maybe you are trying to sell your product online, and you have different web designs to see which one of them lead to more sales or more conversions. Or for the same product, 2 different prices to see which of them could yield a higher net profit, or on the other hand, which of them could lead to more new customers. Those are 2 different goals, and depending on the state of your business, you may be in a stage where you are more interested in acquiring more customers, and you may be using different options to do that, or maybe you are an established business and you just want to increase your net profit. Or again, coming back to the medical examples, 2 different therapies to understand which of them may be more effective at suppressing cancer. And normally within the medical context, those 2 options, A and B, are often called the control group and the treatment group, or the control option and the treatment option. The control group is normally the group that is exposed to no treatment or a standard treatment, the current treatment. And the treatment group is the one that is exposed to the new treatment, the one we think is going to be better than no treatment at all or the existing standard treatment. Okay. Moving forward for today, we'll be just using the A and B nomenclature. We'll not be using control and treatment group, but you may hear that nomenclature when it relates to A/B testing and hypothesis testing. Right? So those are general examples. So some more specific examples. There's one famous example from Microsoft, the Bing search engine, that one single A/B test about changing the way the Bing search engine displayed ad headlines led to a 12% increase in revenue. And that was equivalent to more than $100 million per year in the US alone. So that's a very famous example of where one A/B test led to a huge profit. Okay? And actually, the story is that A/B test had been proposed for someone, and it was kind of people did not act on it, and then someone decided, oh, this may be a good A/B test, and they did it, and then they realized it was a very profitable one. An example from Amazon, and this one you may be familiar if you use Amazon. Nowadays, you'll see practically all the time Amazon offering you a credit card when you go check out your shopping cart. And that didn't happen by accident. In the past, they didn't have that option. They did A/B testing and experiments, and they realized that moving the credit card offers from their home page, where in the past they were, to the shopping cart page, boosted the profits by tens of millions of dollars annually. Okay, so another example of A/B testing increasing, having a huge impact in a business. However, it's not always perfect, and it not always works. Most of the times doesn't work that well. And data from both Google and Bing show that only about 10 to 20% of experiments actually generate positive results, in the sense they actually are implemented in business and translate to improvement in business. And all of these stories, you can read them in this article, The Surprise Power of Online Experiments, published in the Harvard Business Review in 2017. You'll have all these slides after today. We'll send all the materials to you by email, so you'll have all of these. And these are links where you can click, and you'll be directed to that source. All right. So A/B tests can be very powerful, but how are they done? Okay. Actually, that's a good question. Maybe some of you already have an idea of what are A/B tests. Let's just check what's everybody's understand of how an A/B test is done. So if you could just think, you can answer the question on your head, try to write by yourself in a paper, or try to answer in the chat, share with us what you think are the steps of an A/B test. I'll give you a moment for you to think what are the steps of an A/B test, just the general steps. They should fit in your hand, up to 5 steps would be fine, or whichever way you understand A/B test. All right, hypothesis test, great. All right. So I'm going to give you my my answer, and here we go. So this is how I break down the process of doing an A/B test, and we are going to focus more on the operational ones, the steps 1 to 4. Okay? We're going to cover these ones in detail. But before you start an A/B test, you actually have to define the A/B test. So there's a kind of call it step 0, where you come up with some idea for an A/B test and you define the A/B test. What's your question? What's your goal? What data do you have access? What subjects will you be using for your A/B test? What are the options that you're going to be testing? And what's the test statistic? The thing that you're going to be measuring to compare the two options to see if they are actually different or not. Okay. So that's a very important step, the definition step, where you define what's the A/B test that you want to do. What we're going to focus more today is in the operational part of it. Once you know what you want to do, how is it done? Okay. So you need to have a set of subjects that you can use for your A/B test. So identify a set of subjects that you'll use for the A/B test, the whole set of subjects. Then that's step 1. Step 2 is to randomly assign those subjects to the 2 separate groups that we call A and B. And it's very important that you assign those subjects to the groups randomly. Step 3 is to expose each of the groups to the different treatments or the different options, A and B, and measure the results. How do they perform in terms of your test statistics? Okay? And then step 4 is the one of actually performing the hypothesis test to determine if the observed difference is statistically significant or not. And this one for today we'll be doing with the permutation test. We'll be showing it how to do hypothesis testing with permutation test today. And finally, kind of a step 5 that we are not going to be discussing much today as well is taking action or making a decision and potentially taking action based on the test results. If the test results are good enough, you'll decide on implementing that change in your business and actually take the action of making that change and get the benefits of that test. So that's kind of an overview of the steps. And I will use this animation to kind of illustrate these steps. So first, we need to have a pool of subjects that we identify to use in our A/B test. And in this case is this pool of 20 dots. Each dot represents a person. That's our step 1, where we have all the subjects that we selected to use in our A/B test. Step 2 is this step 2 here. We're going to randomly assign these 20 subjects to 2 separate groups, the group on the top and the group on the bottom. Each of them is going to have 10 people each. So let's randomly assign them. And you see there was randomization in the way the bullets were assigned to the 2 different groups. Okay? Now we have 2 different groups, A and B, each of them in this case with 10 people each. And the step 3 is to actually subject those people or those subjects in the groups to the treatments. The treatment A here represented with the purple color, and the treatment B here represented with the yellow color, and see what happens. Will they convert or not? So in this case, we're just talking about a yes or no. Is the person going to click on your ad, going to buy your product, or no? So we're just talking about conversion rates, and we'll just be talking about the yes conversion rate. And that's when we subject them to the different treatments, and then we see that some people, the red ones, did not convert, and the green ones did convert. And now what you have to do is go to each group and count within each group how many of them did convert. In this case, for group A, if you count, we'll have 4, 6, 7 greens. So we have 7 out of 10. That's a 70% conversion rate. And for B, we had 1, 2, 3, 4 greens, 4 conversions, and that's 4 out of 10. That's a 40% conversion rate. So we did our A/B test where we split a total set of 20 subjects into 2 groups, A and B. We sent 10 people to each of the groups. So the group A had 10 people, group B had 10 people, and then we subjected each of the groups to the different options, the B and the A. And for B, we had a 40% conversion rate. 4 people out of the 10 converted, like they bought our product, clicked our ad, and so on. And for group A, we had a 70% conversion rate. 7 people out of the 10 converted. Okay. Now, what we were interested in is the difference between the 2 options. In this case, the difference between A and B is going to be 70% minus 40%, and that is 30%. Okay. So that's the end of step 3. We measured the test statistic, and now we see there's a difference of 30% between option A and option B. Now the question is, step 4, is that difference statistically significant or not? And to do that, we need to do hypothesis testing, and we'll be doing it with the permutation test. So that's what's coming next now. All right, so here's a summary table of this little experiment that we just conducted. And we are using this small experiment with small numbers so that we can see everything. We can see all the subjects moving around through the process, and we can compute everything from scratch. And you'll be able to see all the code working and all the solutions happening real time. Okay? Normally, an A/B test does not use these small numbers. You need larger numbers. Okay? We're just using these small numbers so that we can compute everything and understand everything very easily. So we have our A/B test. We have 10 people in option A and 10 people in option B. We subjected them to the different options, and we noticed that from option A, we had 7 yeses and 3 no's. That's a total of 10. And for option B, we had 4 yeses and 6 no's. So the conversion rate, yes rate for A was 70%. Which is 7 over 10. And we'll just keep talking about percentages. This is 0.7 over 10 is 0.7, but in percentage, 70%. And the conversion rate, yes rate for the group B was 4 in 10, that is 40%. Okay? Now, our test statistic, the thing that we are using to measure if there's a real difference or not, is the difference in the yes rate. And the difference is, we are defining it as A minus B, so 70 minus 40, and 70 minus 40 is 30%. Okay, so this is our observed difference. We did the A/B test experiment. We selected the subjects. We assigned the subjects randomly. We subjected them to different options A and B, and we measured for each group what was the conversion rate. And for A was 70%, for B was 40%. The difference between A and B is 30%. Now the question is this difference statistically significant or not. Okay, and basically what we want to understand to answer this question is this difference that we see here of 30% due to a real difference between the options A and B, or could it just be due to random chance alone? Okay, and that's what hypothesis testing is going to do for us. And here's another kind of view of how the A/B test works in the perspective of a subject that's participating in an A/B test. So this subject one, this person one, was randomly assigned to group A, and then when subjected to the option A, it actually converted. So this was someone that, say, bought our product or clicked in our ad. But for example, person two, this person two was also randomly assigned to group A and did not convert, was a red one. And person three was randomly assigned to group B and it converted, and so on and so forth. So you get another view of how an A/B test works. Okay? People are randomly assigned to groups, and then within each group, they are exposed to the option, the corresponding option, the A and B, and we measure if they convert or do not convert. And then in the end, we calculate how many of them actually converted, and we're computing the difference of the conversion rates between group A and B. And that's our test statistic, the difference of conversion rates between A and B. Okay, so now we get to the step 4, which is the hypothesis testing. And again, in hypothesis testing, we are trying to understand if the observed difference, in this case, the 30% difference between the two groups, is statistically significant or not. Okay. Now, thanks to the step 2, which was randomization, the fact that we assigned the people to different groups randomly, we can say that any difference that we see between A and B can only be due to one of two options. Due to random chance, it just so happened that by the OR randomization put everyone that will say would naturally or for whatever reason always say yes in one group, and then the people that would always say no in another group. So by random chance, you can get some difference that is just due to random chance, just by the randomization that we use to assign the subjects to different groups. And that's the null hypothesis. Or if it's not due to random chance, the alternative is that it is due to a real difference between the options A and B. So there's something actually important in the significant and important difference between groups A and B, the options A and B, that make it so that people in one group are more likely to convert than people in the other group. In the example, or in the medical example, between two drugs, say, or two different treatments, maybe one treatment is actually much better than the other at treating a certain disease. Okay? And the idea that the difference we observed is just due to random chance is the null hypothesis. And the other hypothesis is called the alternative hypothesis, that it's actually due to some real difference. Okay, so thanks to the fact that we use randomization, the assignment of people to different groups, now we can test that any difference we observed is either due to random chance or to a real difference between the two options. And the hypothesis that the difference we observe is just due to random chance, it's the null hypothesis. And the hypothesis that the difference that we observe is due to real difference is the alternative hypothesis. And the hypothesis testing is a way of testing which of these may be. Okay? Actually, more technically, what we'll be doing in hypothesis testing will be assuming that the random chance, the null hypothesis, is true, and we'll be measuring a statistic that will tell us if we should keep assuming that the null hypothesis is true or we should reject the null hypothesis. Okay? So during hypothesis testing, what we are trying to answer is the question is to whether random chance, the null hypothesis, could be the null hypothesis alone, the random chance alone, could be a reasonable explanation for the observed difference that we are seeing in our experiment. Okay? So during the hypothesis testing process, we'll assume that null hypothesis is true. We'll create the model that corresponds to the null hypothesis, which is a probability model that we are representing here in this graph, and I'll explain in a moment. And we'll test whether the observed difference that we see in our experiment would be a reasonable outcome under the null model, that it would be just due to random chance. Okay? Or in other words, is the observed difference within the random variability of the null model. And well, we're going to do this step by step, and we're going to use code to understand these concepts better. Okay? So in hypothesis testing, we are trying to understand if the null hypothesis is true or not. And the null hypothesis is normally that there is no difference between the groups, that A and B are the same. So the null hypothesis is that A is equal to B, the option A is equal to the option B. There's no real difference between the two of them. The alternative hypothesis is that no, there is a difference between A and B. A and B are actually different, and the difference we are observing is due to the difference in A and B. So normally when we talk about null hypothesis and hypothesis testing, we are talking about this formulation of either A is the same as B or A is different than B. Okay? And this is what's called a two-way test or a two-way hypothesis test. There is another version, which is the one-way test, the one-way hypothesis test, where we are not testing whether the options are the same or different. We are testing whether one is better than the other. So if we are trying to test if, say, A is better than B, that is our alternative hypothesis. The null hypothesis has to be the complementary. So the null hypothesis that A is worse or the same as B. So A is not better than B is the null hypothesis in our one-way test. And the alternative hypothesis in our one-way test is that A is better than B. Okay? In our experiment, we observed that A was better than 30%. So we can also test the one-way hypothesis test if it's really a significant difference between A and B or not, if A is really better than B or not. Okay? And we'll do the two versions. We'll do the two-way hypothesis test, and we'll do the one-way hypothesis test. Okay? All right. I will explain this graph later, but what this graph represents, this is the density plot, and the density line, this line, represents the null hypothesis. The expected output of an experiment like the one we did, comparing those two groups, A and B, just due to random chance. What differences would you expect to see between the groups A and B, if just due to random chance, just by assigning the subjects randomly multiple times? Okay? And what you'll see here in the red line, the vertical red line, is the observed value of 30%. This is 30% here. And on the other hand, what you see is the minus 30%. And on orange, you'll see and you'll understand that this orange area is actually the p-value. The orange area represents all the values that we could get just due to random chance that are larger, more extreme than the one we observed. So if here's 30% that we observed, all of these values are larger than 30%. They are more extreme than the one we observed. And those are the values that count for computing the p-value. And similarly, all the ones that are smaller than minus 30% would also be more extreme for the two-way test. Okay? So we'll see and we'll understand better that in the two-way test, we are computing the area of these values here, the orange values on the left and on the right, and those two areas together are the p-value. For the one-way hypothesis test, we'll be computing this area only on the right, the orange area on the right, and that area will be the p-value. And the overall area under this curve is 1. That's the overall probability. And then these orange areas are the probability of obtaining values that are as extreme or more extreme than one we observed. And we'll do that step by step, and we'll understand better what it means. Okay. All right. So a little bit more detail about what's the p-value and what else is involved in doing a hypothesis test. Okay. So the p-value is a concept that's very important, but it's often difficult to understand and it's sometimes misunderstood. And here's the definition of what the p-value is, and I will again keep explaining and illustrating many times how this area in orange is the p-value. Okay? The p-value is contingent to your null hypothesis. So given the random chance or the probability model that represents or embodies or your null hypothesis, and remember the null hypothesis that there's no difference between the two options, the p-value is the probability of obtaining results as extreme as the ones that we observed in our experiment. Okay? That's why the p-value is this area in orange. The value that we observed is this vertical line, the 30%, all the ones above that are more extreme, are larger than the 30%. So that area represents all the values that are more extreme than the one we observed, and that's why it represents the p-value. In the one-way hypothesis test, in the two-way, values that are smaller than minus 30% in absolute value, minus 50 is in absolute value is 50, which is larger than 30 that we observed. Okay? That's the meaning of the p-value, and we'll keep repeating it over and over, and we're actually going to compute it with code from scratch, so we'll understand better how it's computed. There's another important concept necessary for hypothesis testing, and that's the concept of significance level, which is often abbreviated by alpha, the Greek letter alpha. The significance level is the probability threshold that we accept for unusual or extreme values. Okay? Often is used as 5% or 0.05. And this must be defined before the experiment. It's defined as initial stage where you're actually defining how you're going to do the A/B test. And the significance level and the value alpha is the probability of that we accept for committing a type 1 error. A type 1 error is a false positive, as in here. The type 1 error is a false positive, and it is when we mistakenly we make the wrong conclusion that an effect is real when in reality it's just due to chance. Okay? So if we use a significance level of 0.05, which is the same as 5%, we are accepting a 5% chance of making a false positive or a type 1 error, which is to make the wrong conclusion that there is a real effect between the two options A and B, when in reality there is no real effect between options A and B. They were just due to chance. So how do we make the conclusion in hypothesis testing? How do we make the decision of whether go with the null hypothesis or the alternative hypothesis? It's by comparing these two values, the significance level alpha with the p-value. Okay? If our p-value is larger or equal than alpha, we retain the null hypothesis and conclude that the observed difference is just due to random chance. There's no real difference between A and B. However, on the other hand, if the p-value is smaller than alpha, then we reject the null hypothesis and we conclude in favor of the alternative hypothesis that indeed there is a real difference between options A and B, and the difference that we observed in our experiment is due to a real difference between options A and B. Okay? So what does it mean, the p-value being larger than alpha? Again, the p-value is the probability of obtaining values that are as extreme or more extreme than one you observe. If there's a high probability of us observing very, very extreme values, then there's a high probability of the difference we observed be just due to random chance. That's why we conclude that with a large p-value, the difference that we observe is just due to random chance, is not really due to a real difference between A and B. Okay? And we need this significance level alpha to make the decision, right? We need to, the alpha is the one that tells us, okay, what's a large p-value and what's a small p-value, okay? If you use 5% for the alpha, that is the threshold for the p-value. If the p-value is larger or equal than 5%, then we retain the null hypothesis. If the p-value is smaller than the 5%, then we reject the null hypothesis in favor of the alternative hypothesis, okay? So those are the main concepts in hypothesis test. The p-value, the significance level, and how they are used to make the decision. And their meaning. The alpha, the significance level, is the probability that we accept of making a false positive, a type 1 error, okay? To make the wrong conclusion that there's a real effect, that there's a real difference when in reality there is not, and it's just due to chance. The p-value is the probability of obtaining results as extreme as the observed ones, just due to random chance. So the decision is, if there's a high probability of observing a result like that just due to random chance, then we conclude that the result we observe is just due to random chance. If there's a very low probability of observing such a result due just to random chance, then we conclude, okay, this is not just random chance. This is a real difference between A and B. Okay? So that's the base of how hypothesis testing is done and how the decision is made. Now, we need to compute the p-value, right? The alpha, the significance level, we set at a certain threshold. It's common to use 5%, but we need to compute the p-value. Okay, and now I'm going to show you how to compute the p-value. And notice we talked about the type 1 error because that's the type 1 error, or the false positive, has a probability of alpha, or significance level. There's also a type 2 error, which is the complementary, false negative, when we wrongly conclude that there is an effect, or that the difference we observed was due to chance when it was actually real. So we can have these two types of errors, the type 1 error, which is false positive, and the type 2 error, which is the false negative. The false positive is related to the significance level. Indeed, it's the probability of a false positive is the significance level itself, alpha. Okay. Right. Okay, so we need to compute the p-value. And how can we compute the p-value? Well, one way is to use some classic statistical tests, but we're not going to do that. We're going to use this method, this permutation method, because it's a way to understand and see how the p-value is actually computed. Okay? So permutation test is a resampled procedure that is used for hypothesis testing. What's resampling is to repeatedly sample the values that we have in our observed data to assess or determine the statistics of a random the random variability of our statistic. In our case, the statistic metric that we're using to compare the option A and B. There are two main types of resampling procedures. Bootstrap is resampling with replacement. When you have your data and you do resampling, when you take one, imagine that you have all your data as each data point is a ball, and you put all the balls in a bag. And resampling is basically going inside the bag and taking one of the balls and looking at it and see what it is. And you can do resampling with or without replacement. With replacement is when you go to your bag and take one ball, which is one data point, you look at it, you take note, and then you put it back in. So it's available for the next time you go to get a new one. Resampling without replacement is when you have all your data in a bag, you take one ball, which is one data point, and then you take note of what you took out of the bag and you put it away. That doesn't go back in the bag, doesn't become again available for the next draw. Okay? So Bootstrap is a resampling with replacement, where you take a ball, look at it, and put it back in, so it's available for the next time. And Permutation is resampling without replacement. You take a ball, you look at it, and you put it away. So now you have less balls to take from. Okay? Permutation is the one that is used for hypothesis testing. And bootstrapping is used for other purposes, such as assessing the reliability of a statistical estimate, like in your statistical models. We're going to be talking about permutation and permutation test. So the permutation test is a resampled procedure that we use to do hypothesis testing, and we're going to explain it step by step, so you'll see in action. Okay. So in more detail, it's kind of the process of combining two or more data samples. In our case, we're going to use our two data samples together and randomly relocate those samples to new resamples so that we can see how the test statistic varies as we do this resampling procedure. You're going to see that in action. It's better to understand. I'm going to explain and show you examples. It's going to be better. It's going to be easier to see in the next slide. Okay. So for us, the permutation test is going to be a way to create the null model. So the p-value is computed from the new model, and the new model is kind of what variability would they expect in our test statistics just due to random chance. And that's what the permutation test gives us. Okay? Okay. So the advantage of the permutation test, especially over the classic statistical tests, is that it makes no assumptions. The permutation test makes no assumption about the test. There's no assumptions of normality or any other assumptions. The null model is created directly from the data itself, and you'll see how it's done next. Okay? So that's one big advantage of the permutation test. All right, I have here an explanation of how the permutation test is done, kind of broken down by individual steps. Okay. Remember, the permutation test is now what we are using to do what was step 4 of an A/B test, which is the hypothesis testing part to compute the p-value. Okay, but the permutation test itself has a whole procedure for doing it, and we start with kind of step 0 having the A/B test results, and here we have in our step 0 the A/B test results. So we had 2 groups, and in group A we got these results where we have 70% of the people converted, so we have 7 greens. And in group B, we have the 40% conversions, we have 4 greens. That's the starting point for a permutation test. Okay? The first step in our permutation test is to put all these results that are currently separated in 2 groups, the A and B, together in a single data set, in a bag. And I'm going to do that by putting them all here in step 1, going to put all of them together in one bag. And I'm even going to order them, the greens and the reds, so it's easy to see how many we have in total. So in total, when we combine A and B, we have 11 greens and 9 reds, because we had 7 greens from A and 4 greens from B. 7 plus 4 is 11. Okay? So now what we did in step 1 was we had these A/B test results, the results for A and the results for B, and we put them all together in a single bag. There's no separation anymore. They are all together in a single bag. And now the step 2, the steps 2 to 5 is to perform one permutation. And now you'll understand what the permutation is. A permutation is take the balls from the bag randomly take a set of balls from the bag and assign it to group A, and then take another random set of balls from the bag and assign it to group B. Okay, so if you will, in kind of more broken down, is first we will shuffle the bag, we'll randomize this bag, and then we draw a random sample without replacement for group A, and after that we do another random sample without replacement for group B. Okay? And finally we measure the test statistic, the difference between A and B. And that's what I'm going to do now from this step 1, where we have all the balls in the bag, to the one permutation that we have here, the steps 2 and 5 to 5 altogether. So I'm randomly assigning all the balls that were in the bag to be a resample for group A and a resample for group B. And now we measure again our statistics. So for A now we got 5 greens, so that's a 50% conversion rate. And for B we got 6 greens, that's a 60% conversion rate. And now the difference between A and B is 50% minus 60%, that is minus 10%. So this is one permutation only. Okay? In the permutation test, what we're going to do is this process many times. We're going to do many permutations, and at each permutation, we're going to get a value for our statistic. In this case, we got minus 10. And as we do more permutations, each of them randomly, we'll get more values, and every time it's a random value. And with all those values, we'll be able to create the density plot of the null model, the null hypothesis. Okay? So that's one permutation. And then step 6 is to do many permutations, basically repeat those steps 2 to 5 many times. At each time, we record the test statistic, and then we'll use all those test statistics to create the probability model that represents the null hypothesis. Okay? And for the hypothesis test, we'll use all those results to compute the p-value. We'll have the null model, the probability model for the null hypothesis, and then we'll be able to compute the p-value as the ratio of all the values that we got that are as extreme or more extreme than the ones we observed. And again, we're going to show you and compute that from scratch so you can see how it works. Okay. Right. The other perspective of how the permutation test works, like from the perspective of one individual involved in the process. So you can think of this person that was in our results, a green result in group A. We put it in the bag with all the others, and then we just happen to be randomly assigned back to A. But say another person, this person that was in our results in group A went into the bag, and then when we did the resampling, ended up in group B. Okay? And so on and so forth, right? People are randomly assigned or data is randomly assigned to the different groups A and B, and points that were from A could end up in A again, or then end up in B, and so on, and vice versa. Okay. All right. So suppose we did that process, okay, of permutation, the permutation process, this process, 100 times. So we did it one time, we got minus 10%. Now we do it, put all the balls in the bag, do another resampling, and then you'd get another different, you could get again minus 10% or a different value, and so on and so forth. And we're going to do that 100 times. Each time we get a value for our statistic. Okay. And this is the results that we got. So I did 100 permutations, and we're going to do this in code. You'll see it in action. And I got these values. I got minus 50, minus 30, minus 10, 10, 30, and 50. And I got minus 50 4 times, minus 30 12 times, minus 10 30 times, 10 33 times, 30 16 times, and 50 5 times. So this is the table of our permutation results, and is represented here in this bar chart. Okay? In this bar chart, what you have in the horizontal axis is the test statistic, the minus 50, minus 30, minus 10, 10, 30, and 50. And the height of the bar are the counts of how many times did we get that in our permutation results. And under the null hypothesis, there's no difference, so you get more results around 0. Okay, so you get more results for minus 10, for 10. Okay, but we got quite a few results that are as extreme or more extreme than our results. So this is where our observed result, when we did our experiment, we observed the difference between A and B of 30%. And now these are the results that are as extreme or more extreme than the 30%. Okay? We got 16 30% again, that is as extreme of 30% itself. And we even got 5 50% differences where A is 50% better than B. Okay? So these are the values these are the counts that we'll be using to compute the p-value. Okay? These ones we use for like the one-sided or the one-way test, but we also need to consider these other ones on the lower end for the two-way hypothesis test, because minus 30 is as extreme as 30. In this case, minus 30 is saying that B is better than B by 30%. B is better than A by 30%. Okay? Or 30% here is saying that A is better than B by 30%. Minus 30 would mean that B itself is better than A by 30%. Okay? And minus 50 is also more extreme than the 30%. So for the two-way test, if you recall, the null hypothesis is that there is no difference between A and B. A and B are the same. The alternative hypothesis is that A is different than B. There's a difference between A and B. So for the two, how can we compute the p-value for the two-way hypothesis test? We need to look at all the results we got from the permutation, all the counts, and we need to find the results that were as extreme or more extreme than the one we observed. So we observed 30%. Which of these values are as extreme or more extreme than 30%? Well, 30% itself and 50%. So these 16 and 5 count. So we need to add the 16 and the 5. But because we are doing a two-way hypothesis test, we also want the other side of the negative values that can be as extreme or more extreme than 30%. And we have the minus 50 and minus 30. So we also need to count these 4 minus 50s and these 12 minus 30s. So the total count of extreme values that are as extreme or more extreme than one we observed, the 30%, are the 4 times we got minus 50, the 12 times we got minus 30, the 16 times we got 30, and the 5 times we got 50. And that's what we are summing here. 4 plus 12 plus 16 plus 5. Those are all the counts of values we got in our permutation test that are as extreme or more extreme than what we observed in our A/B test experiment. Okay? And when you sum all of that, you get 37. Okay? So in 100 permutations, where we kind of simulated the same process 100 times, we got 37 of those 100 values that are as extreme or more extreme than when we actually observed in our experiment. Now we can use that to compute the p-value as simply the ratio of those counts of extreme values by the total number of times we did the process. So our p-value is going to be 37 over 100. 37 are the counts of extreme values. 100 is the total number of times we did this process. the total number of values we got in our permutation test. So that's the p-value in a two-way hypothesis test, is the ratio of, or the probability of values that we would obtain in a process like this just due to random chance. The one-way test, our null hypothesis that A is not better than B, so A is either worse or the same as B, and the alternative hypothesis that A is actually better than B. So for the one-way test, the extreme values are only the extreme positives in this case, because we have A being better than B by 30%. So these are the only extreme values are these, okay, where A can be as better than B as it is when we observed it. So for the one-way test, we count the 16 plus the 5, and those are the number of extreme values, the 21, add up to 21, and the p-value is going to be that those counts of extreme values divided by the total counts of times we did this process, the total number of values we obtained through the permutation test. So it's 21 over 100, and that's 0.21. So we computed the p-value through a permutation test, and we got the p-value for the two-way hypothesis test as 0.37, and the p-value for the one-way hypothesis test as 0.21. Okay. So now what's the decision? Well, the decision is, our p-value for any of these is very large, is larger than our alpha of 0.05. So the conclusion is that we have to retain the null hypothesis, that the observed difference is due just to random chance and is not due to real difference between A and B. Okay. So that reaches the conclusion of the hypothesis testing part through a permutation test. So we did a permutation test, we got these counts of the results for the permutation test. Now we can look at them and see how many of them were as extreme or more extreme than what we observed, which was the 30% in the very beginning. And we can use those counts to compute the p-value. Basically, the p-value is the ratio of, or the probability or fraction of values that are as extreme or more extreme than that 30% we observed. And they are highlighted here, the p-values are highlighted here in orange because these minus 50 and minus 30 and the 30 and the 50 are the values that are as extreme or more extreme than 30%. And it's these counts of the heights of these bars that contribute to the p-value. These ones in the middle are less extreme than the 30% we observed, so they do not count for the p-value. This is the bar chart version of it, and this is the equivalent density plot. Okay? And again, here we have the vertical red line at 30% and the dashed red line at minus 30%. So all the orange area corresponds to the values that are larger than the 30% or smaller than minus 30%. And those areas represent the p-value. Okay. All right. Okay. So let's do this with code now. So that was kind of an explanation of the concepts, and we use some data visualizations to try to understand better those concepts. We're going to actually code these kind of from scratch using both R and Python separately. And I'll be using R on the left and Python on the right. So R is going to be, the code is going to be with the gray background, and Python is going to be with the yellow background. Okay? Right. So I'll be using some packages just for convenience. Most of it is just going to be done in R, is going to be done in base R, and in Python is going to be done mostly in base Python as well. Okay. Although we do need some like sample function from the random package, and I'll be using some functionality from pandas as well, just to make our life a little easier. All right, so let's try to reproduce these by code so we can see how it works. First, I'm going to define some variables that define our problem. And if you recall, we had a total of 20 subjects. So T is a variable, and I'm assigning to it the value 20. And T is a variable that represents the total number of subjects, the A and B, the total of A and B. And we assigned 20 of those, 10 of those to A and 10 of those to B. So the size of group A is equal to 10, and the size of group B is also equal to 10. Okay? So A, the variable A, is the number of subjects in A, and B is the number of subjects in B. Now, we had, in our experiment, the observed experiment, we had 7 people saying yes in group A and 4 people saying yes in group B. Okay? So A underscore yes is the variable that contains the number of people that said yes in group A, and B underscore yes is the number of people that said yes in group B. So these variables fully define our experiment. Okay? And now we can compute a few other results from our A/B testing experiment. In particular, we can compute the total number of yeses, which is the sum of these two variables, the AS and the BS. So the total number of yeses is AS plus BS. And the total number of no's is going to be T, which is the total number of people, minus the TS, which is the total number of yeses. And what we are interested in is in the conversion rate. So this AS percentage is the ratio of the count of yeses by the total number of people in A multiplied by 100 to be a percentage. And the same for B. BS PC, PC short for percentage, is the percentage of yes in B. So our test statistic, the metric we are using to compare the groups, is the difference between A and B, the AS percent minus the BS percent. And I'm assigning that result to a new value called AB underscore yes percent. And I'm printing here all the results. So this cut is just a convenient way of printing the results in a nice format. And the observed yes rate is 70% for A, 40% for B, and the A minus B is 30%, which is 70 minus 40. And just to recap, the total counts for yes and no's, we had a total of 11 yeses and a total of 9 no's. So that's just the code in R, base R, to define the problem and compute some additional results that are going to be useful moving forward. And here's the equivalent code in Python. Actually, it's very similar. So in Python, the assignment operator is always equals. In R, you can use equals or the left arrow assignment. In R, I'll be using the equal assignment so that it shows that the similarity between R and Python. But all this code is the same, just assigning values to variables. And this one is also the same, just using those variables to compute new results and assigning those new results to other variables. And this one's also the same. And here, just slightly different. In Python, I'm using the print function to print the message that I want in the end. And I'm just printing it so that it prints similarly to what is on the left in R. Okay. R also has a print function, but is less convenient. Cat is a function that does concatenation and printing all together. So first concatenates the expressions, and then it prints them to the output. So that's why it's more convenient to use cat here. And again, we have the same experiment, 70% yes for A, 40% yes for B, a difference of A minus B of 30%, and a total of 11 yeses and a total of 9 no's. So this is just setting the stage and defining the problem. And you can see here how we use variables to assign values to variables, and then we use those variables to make computations, and we assign the results of those computations to new variables. All right. Sorry, I just saw the comments that is the slide still blurry? Okay, it's fine now. Good. Okay. Right. So next, I'm going to show you how to make one permutation. Just one, and then we'll use these to make many permutations. Okay? And I'm going to recap the steps for doing a permutation. I'm just setting the seed, the random seed, so that these results are reproducible. Every time you repeat them, they are still random, but they are the same random results. Okay? So if you recall, the first step to do a permutation is to put all the results in a bag. And that's what I'm doing here. I'm putting all the results in a vector, and 1 represents the yeses and 0 represents no. So before in our visualizations, I was representing the yes with the green ball and the no with the red ball. Now I'm representing a yes with the number 1 and the no with the number 0. And this C is the combine function that is used to create vectors in R, and rep is the repetition function that is used to make repetitions of in this case, the number 1. So we are repeating the number 1 a certain number of times. How many times? The total number of yeses that we had in our data. And then we are repeating the number 0 a total number of times that we had nodes in our data. So this creates a vector of 1s and 0s with the amount of 1s being the total number of yeses in our data and the amount of 0s being the total number of nodes in our data. And I'm assigning this vector to a variable called bag1. And actually, it's the one I'm printing here. So you can see that bag1 is a vector of 11 1s and 9 zeros. So this creates a vector of 11 1s followed by 9 zeros. And that's the first step of putting all the results of our A/B test in a bag. In this case, our bag is a vector. Second step is shuffle the bag. Okay, so for the randomization process, I'm using the sample function from base R to sample bag1, and I'm just assigning that to a new variable bag2, so that in the end I can print them both separately. And here is the shuffled bag now. It's this one. So we started by putting all the results in our bag1, and I put them by order so we can see that indeed we have the expected number of 1s, expected number of 0s. And in step 2, we shuffled the bag, and now this is the bag with the same amount of 1s and 0s, but now shuffled in a random order. Okay, that's step 2. Step 3 is to take a random sample of size of group A, and because the bag was already randomized, I'm just going to take the first A elements of the bag of the vector to represent the random sample for A, and then I'll take the remainder elements of the vector of the shuffled vector of the shuffled bag to be the random sample for B. Okay? And here I'm using the square bracket notation to slice a vector to select the elements from 1 up to A. Remember, A is the number of people in group A. And R starts indexing or counting at 1, so that's why the first index is 1. Python starts indexing at 0. We don't use it explicitly there, but that's an important difference between R and Python. Okay, and then this is just a way of selecting the remainder of the results we have in the bag after we take the random sample for A to assign it to the vector for B, the random sample for B. Indeed, you can see them here. And you can see that the random sample for A is the first part of our shuffled bag. Okay, you see it's exactly the same. And the random sample for B, this one is the last part of the shuffled bag, the exact same. So we are able to get a resample for A and a resample for B. And now we can compute our statistics. So we go to the resample for A, and we're going to count the number of yeses. And how many yeses did we get? We get 4 plus 1. We got 5 yeses. That's a 50% rate, 5 in 10. And then we go check B, and in B we got 1, 2, 3, 4, 5, 6. That's a 60% yes rate. So the difference between A and B is 50% minus 60%, which is minus 10. Okay? The same thing that we got when we did that visualization explanation. And as a reminder, the observed difference, the one that we actually observed in our real A/B test experiment, was 30%. But now this permutation gave us minus 10. So when we did our experiment, we observed that A was better than B by 30%. When we did this permutation, we see that by random chance, B could be better than A by 10%. Okay? But this is just one permutation. Okay? We need to do many permutations. That's what's coming next. Before I show you that, let me just show you the equivalent code in Python. Here we set the seed, again, the random seed in Python, so that the results are also reproducible while still being random. Here is a way of creating a bag. In this case, is a list, a list of 1s and 0s. The 1s as many as there are total yeses in our data, and the 0s as many as there are total no's in our data. So this creates the bag, the initial bag, which is this list. Again, a list of 1s and 0s, 11 1s, which was the total number of 1s or yeses in our data, and 9 0s, which was the total number of no's in our data. Now we're going to use the sample function similar to the sample function in R to shuffle the bag and assign those results to bag 2. And here's the list representing our shuffled bag. As you can see, it's randomized now. And as we did there, we're going to take the first part of bag2. And here we can just use this short notation, colon A, to get all the elements starting at index 0 up to index A, which is the number of people in the group A. And we're going to assign that to A underscore RS, the random sample for A. And then we're going to get the remainder of the bag2 after A, after index A, to be the random sample for B. Okay? And you'll see here's the random sample for A, and you'll see that this list has the exact same elements that are the first part of the shuffled bag. And then for B, we get this other list, which are the exact same elements as the second part of the shuffled bag. Okay? And then we can compute the statistics. Again, go check the resample. How many yeses did we get? We got 50 again, five yeses, that's 50%. And for B, we got 6 yeses, that's 60%. So the difference between A and B is minus 10%, 50 minus 60 is minus 10%, as in the other example. So that's how we could do just one permutation, both with R and in Python. Now let's see, we need to do this many, many times. How can we do that with code? And here's how we can do that. Again, we start by setting the seed to make results reproducible, and by putting all the results in our bag. Okay, and the bag is a bag of 1s and 0s. Now we need to do the step 6 of the permutation test, which is to repeat the previous steps 2 to 5 a large number of times, to do many permutations. How many? Well, I'm going to set this parameter p as being the number of permutations that we'll be doing, and we'll be doing 100 permutations. Okay? I'm going to create this initial vector, which is going to be the vector that's going to contain our results of the permutation, of each permutation. So it's going to be a vector of, it's going to start as a vector of 0s, and when we do each permutation, we're going to update each position of that vector with the corresponding value for the test statistic for that permutation. Now, when we want to repeat the same process many, many times, we use a loop construct. In this case, we're going to use a for loop, and the syntax for a for loop in R is the keyword for, followed within parentheses the variable that we'll be using to iterate over, and in it kind of gives us a range of values to iterate by. So we're going to iterate over 1 up to the value of p, which is 100. So we're going to do a loop operation 100 times. At each time, I is going to take the values of 1 up to 100. So I is going to start with the number 1, and then it's going to be number 2 and number 3, and so on and so forth. And at each iteration, so the curly braces here enclose all the code that's going to be executed at each iteration of the for loop. At each iteration, we're going to shuffle the bag, which is the step 2 of permutation test, and then take a random sample for A, as we did before, that's the step 3. Take the remainder as the random sample for B, that's step 4, and compute the test statistic, which is, again, the difference in the yes percentage for A and the yes percentage for B. Okay? So we're going to do that 100 times. At each time, we're going to save the result, and the result is going to be saved in this perm_res, which is short for permutation result. And in the end, I'm printing here the results, and you can see that in the end we have 100 numbers. Okay? These are 100 numbers, and they are random numbers. That 10, minus 10, 10, minus 30, and those are the numbers that we get through the permutation test process. Okay? And these are the numbers that next we'll be using to compute the p-value. We can do the same in Python. Again, set the seed, create a bag with all the data from our experiment, set the number of permutations that we're going to do, 100 again, create an initial list of 100 zeros, okay, where we're going to update it to save the results. And we're going to use another also for loop. The syntax is slightly different. You can see here that the syntax for Python for a for loop is the keyword for, and then the variable for your loop in, and here I'm using the range function to define the range to iterate over. So this defines a range of 100 elements. In this case, they are actually the numbers 0 to 99, but that's just a detail because Python starts indexing at 0. And again, at each step, we shuffle the bag with the sample function, and we take the first part of the bag to be the random sample for A. We take the remainder part of the bag to be the random sample for B, and we compute our test statistic, which is the % yes rate for A minus the % yes rate for B, and we assign that to the corresponding element in the list. Okay? And in the end, we print here the results. Now, printing here is a little more tricky to make the printing work nice in these slides. So you don't need to worry about these details. It's just a way of printing the results so that we can see all of them. But you can see that there are also 100 numbers, and each of them comes from a permutation. And altogether, they will let us compute the p-value. They represent the null hypothesis or the probability model of the null hypothesis, and we can use them to compute the p-value. Okay. So we did or many permutations, in this case, 100 permutations. We got the 100 values that we can use to that represent the model of the null hypothesis, and now we can use these values to compute the p-value. And I'm going to show you how to use code to compute the p-value now from these results. Okay. So in R, we can use the table function to make the count, to get the counts of our results, and we can see that as we add in our data visualization explanation, and we add 4 times the number minus 50, 12 times the numbers minus 30, 30 times the number minus 10, 33 times the number 10, 16 times 30, and 5 times you got 50 as our test statistic. And now we're going to use these counts to compute the p-value. Again, the p-value is going to be the ratio of values that are extreme or more extreme than one we observed. We observed 30, so these 16 and 5 are extreme counts, and these 4 and 12 are also extreme counts for the 2A hypothesis test. Okay, so for the 2A hypothesis test, what we want are all the values that are in absolute terms larger or equal than our observed values. So the perm results is a vector, with all the results from the permutation test. The ABS underscore PC is the observed difference between A and B in our A/B test. Okay? So what we want is all the values in this vector that in absolute terms are larger or equal than our observed difference in our A/B test experiment, which was 30%. And then we're going to sum all of those. Okay? So this returns a vector of zeros and ones as to whether each of those values is larger than the observed value. And when we sum all those zeros and ones, you get the count of all the extreme values in our vector. Okay? All right. So, and in the end, this is this extreme count, and you can see that it results in 37, which is this 4 plus 12 plus 16 plus 5. Okay? And the p-value is just that 37 divided by the total number of permutations, which is 100. So 37 over 100 is 0.37. That's the p-value for the 2A hypothesis test. For the 1-way hypothesis test, we want the values that are larger or equal than the observed value itself. Now, not in absolute terms. So the negative ones don't count anymore. We'll just be catching these 16 and 5. 16 plus 5 will be 21. Okay? And then the p-value for the 1-way hypothesis test is the 21 divided by 100, which is 0.21. So this cut, again, is just a nice way, just some code to make the nice printing that you see here. Okay? And this is how you can compute the p-value from the permutation test results, just finding which of those permutation test results were as extreme or more extreme than the observed result in our A/B test experiment. And you can do the same in Python. Now, to do this in Python, it's convenient to transform our results from a list to a pandas series. That's what we're doing here. And this is just a little bit of elaborate code to create the table, the equivalent table, as in R and print it in a nice way, the same way as it was printed in R. You don't have to worry too much about that. But again, in this case, we are using a separate kernel. We are using a Python kernel. So the randomizations happen slightly different. So in Python, we got the minus 50 2 times, and we got minus 30 18 times, and minus 10 31 times, and 10 32 times, and 30 15 times, and 52 times. Okay? Then we can compute get the count of extreme values the same way. Here, to get the absolute values, don't use the absolute function like that in R. We use the absolute method in pandas for the series object, which is now this perm res underscore s is a series in pandas. And we again want to count how many of them are larger or equal than the absolute value of what we observed, which was 30% for the two-way hypothesis test. And for the one-way hypothesis test, we want ones that are larger or equal than what we observed. And this one, we don't use the absolute value. And in this case, it also happens that we also got 37 extreme counts for the two-way hypothesis test, and the p-value is also 0.37. But for the one-way, which is just this side, we got 15 plus 2, which is 17, while here we had gotten 16 plus 5, which was 21. But still, in both situations, we get very large p-values. Okay? So the decision is we have to retain the null hypothesis because the p-values are very large, are larger than 0.05, which would be our alpha standard threshold. Right? And so to recap, again, in using those data visualizations, we did a permutation test. We got discounts of values in our permutation tests, and we used them to compute the p-value as the counts of those values that are as extreme or more extreme than what we observed in our experiment. And this density plot is created from those counts, okay, from that permutation test. And the vertical line represents our observed value, which was -30. The orange area are the values that are larger, more extreme than what we observed. So this orange area represents the p-value. Indeed, the full area under this curve, this density plot, is 1, and this portion in orange it's also probability, and it's the p-value itself. Okay? And it's 37 because it's those 16 plus 5 plus the 4 plus 12 divided by 100 gives you 0.37, the p-value. And you can have this graphical visualization of the p-value as a density plot, or this one as the bar charts as we did before, or this one works as a bar chart because we have very small numbers, very small counts, just for didactical purposes. Normally, what you do would be an histogram like that, not a bar chart. But in the end, what you really want is the density plot. And if you just want to create one visualization of it, the density plot is the one to go with. All right. So that brings us to the end. We did all those steps with code, step by step. And now, just checking how we're doing on time, I could give you something extra. All right. We are a little over time, but I'll just show you briefly. We use the code kind of step by step and different slides at a different part of the code. But once we have this code, we can put it all together in a function, and then we can use that function to do all the work for us in one line. So I created functions to do all this work for us. And in particular, I created this one function, AB permutation test, which I can show you afterwards if you'd like to, that will do all that we did step by step now. So that I can show you different results for different values of AB test experiments. So this AB permutation test is a function that takes in parameters that define our AB test experiment and the number of permutations that we want to do, and it will compute the full permutation test, return the p-value of the permutation test, and show us the graphical visualization of the null hypothesis and the p-value like so. So repeating for the same example we have been doing all along, we have 10 people in the A group. So the AL parameter for this function is the number of people in the A group. The BL is the number of people in B, 10 again. We have 7 yeses in A and 4 yeses in B. And we're going to do NP, the number of permutations, is going to be 100. Okay. And so this is what we observed. This was our experiment. We have a 70% yes rate in A, a 40% yes rate in B, and the difference between A and B is 30%. Now we did 100 permutations, and this is the result we get. We get the p-value of 0.36. It's also represented here as the p-value and graphically represented there. Now I'm going to show you another example where the p-value is much smaller, okay? And also an example that uses much larger numbers. So in this experiment, which is a different experiment, we have 1,000 people in A and 2,000 people in B. You don't have to have the same people in A and B. Normally, you want to have the same people in A and B, but you don't necessarily have to. And in this experiment, we got 30 yeses in A, and we got 100 yeses in B. Okay, now we want to know if this is significant or not. So what we have in terms of conversion rates or yes rates for A, we have 30 over 1,000. That is 30 in 1,000 is 3%. So only 3% of the group A was a yes. And in B is 5%, which is 100 over 2,000. That's 5%. So the difference between A and B is -2. It's 3% minus 5%, that's -2%. In this case, in this experiment, the observed difference was that B was 2% better. Now, the question is this significant or not? We can use this whole process. Now is all being done just in one function. And we see this graphical representation and the p-value here. Now, the p-value is very small. It's smaller than 0.05. So we would conclude that this was not due to random chance. We would conclude in favor of the alternative hypothesis that there is a significant difference between A and B. So even though this difference may look small, right, just a -2% difference, it's actually significant because the p-value is very small. And you can see that a small p-value is now a very small orange area here in the plot. Okay, so in the previous experiment, the one that we did all along, the orange area was very large, the p-value was very large. That represents the proportion of values that are as extreme or more extreme than ones you observed. It's very large. When there's very few values that are as extreme or more extreme than what we observed, that area, the orange area, which is the p-value, is going to be very small. Okay? Indeed, the p-value is really small, is 0.018. That's 1.8%. Okay? All right. We could even play with this in a Shiny app, which I can show you later if you want in a Q&A, but that's the end of it. Okay, so I'll open to Q&A. I hope this was helpful to understand these difficult concepts and to show you that you can code even difficult concepts with very simple code. We just use simple variables, simple operations, multiplication and division and addition and subtraction. And we use for loops, and hopefully you understood how for loops work. So hopefully this was helpful for you to understand these useful concepts that sometimes are difficult to understand. And finally, I'll leave you here, and I can share these on the chat as well, that if you are interested in learning more with us, you can check us on our website. You can check our different programs. We have bootcamps on data science and data analytics. And we also have professional development courses. You can take individual courses or take course bundles, and you can always reach out to our admissions. You can apply to all of these for free, and you get contacted by our team to understand what's the best program for you. Okay, so I'll open now to Q&A, and I'll check what. Okay, I'll share the presentation. You'll get the presentation and all the materials for the presentation by email. Yeah. Okay. Okay, so how long to run an A/B test? That's a good question. And that's related with something we didn't cover. And I'll give you a few pointers, and you'll get these as well. So something we didn't cover in the beginning was, okay, how do you define all the details of the A/B test? And for that, you need to do what's called power analysis. This is more advanced. That's why I didn't talk about it. So when you're defining an A/B test, we need to define, okay, how much data do we actually need? So it's related to how long do you need to run the test. Depends on how much data do you need. And to do that, you do what's called power analysis, where you balance all these four factors. The sample size, which is the number of samples that you'll need to use. If you have all the data, you can use it and do it all already, but sometimes you actually have to wait for the data to come in, and that's going to determine how long you need to wait for data, how many data points do you need. And to make the determination, you need to have, so if you want to determine the sample size, which is a common task, to determine how many points do I need, which is going to tell you how long you need to wait to get all those points. you need to know these other three. You need to define these other three important factors. Okay, you need to define what's the effect size you want to see. The effect size is the minimum size of the effect that you want to detect with your test. For example, you want to be able to detect at least a 10% increase in your yes rate, say your conversion rate or your click rate or your whatever metric you are looking at. And in addition to that, you need to define the power that you want. And the power is the probability of detecting an effect when the effect is actually real. And that's basically the probability of a true positive. And also we need to define the significance level that we already talked about, which is the probability of a false positive. Okay, so to answer the question, how many points do I need? How much time do I need? Because the more points you need, the more time you need to wait. And you need to define beforehand, okay, what's the effect size, the minimum effect size that I want to see? What's the power that I want, the probability of a true positive, and what's the significance level that I'll be using? Once you know these three, once you define these three, it will give you the ideal sample size that you need. Okay. To explain in detail, we'd have to go through that process that we just did, just to explain the p-value, and it would take like a whole another 1 hour or 2 hours. But you can do all of that, of what we did, and all of these power analysis with these packages, the PWR package in R and the stats models package in R. They have functions to do all of the things we did, and also to do this power analysis, where you can define the effect size, the powers, and significance level, and there are functions there that will give you the sample size that you need. Okay, and with that you'll know how much time you need to wait. Important note: the power is the probability of a true positive, and you'll often see it defined as 1 minus beta, where beta is actually the probability of the type 2 error that we talked about, but I didn't mention that was the beta. Okay, so we talked about the type 1 error, that's the false positive, that has a probability of alpha, that's our significance level. The probability of a false negative, the type 2 error, is often called beta, and the power is the inverse of the type 2 error, is the true positive, and the probability of the true positive is 1 minus beta. Right, I hope that answers the question. And there you have references there that you can go to where you have functions that do this for you. So normally we'll not be doing this by hand ourselves. You just go to these packages that have functions ready. Okay, where there's still a black rectangle. Okay. You'll get the slides afterwards. The black rectangle may be the Zoom interface that I'm trying to move away from, but I'm not able to move it away. Okay. Let's see. One way or two way. Oh, whether you do one-way hypothesis test or two-way hypothesis test, that depends on what you want. Are you trying to understand if two things are different or if one thing is better than the other? Normally, people want to know if one is better than the other. So if you want to know if option A is better than option B, then you do one-way hypothesis test. Well, some statisticians say that just to be safe, even when you just want one way, you do the two ways just to be safe, because the two way is more restrictive, right? You'll have more. You have the other side of the tail to account for the p-value. Okay? But if you just want the one way, if you just want to test if one option is better than the other, you could use just the one way. Some statisticians still use the two way just to be safe. All right, just checking if you have any other questions. All right, I think that answers all the questions. Let me give you these links. Okay. All right. I can give you those links. All right. So the code for that you guys can use for answer those questions that you're asking. Those are the links, and the links for our programs are these ones, and the email for our admissions team. So you'll have that. Okay. All right. Any other questions, anyone? Can show you briefly this app. This app shows it's a more interactive way of what we just looked at. Okay? Here you can see that as you change the parameters of your A/B test, okay, you'll impact the p-value you get. So here what you have is 100 people in A where 30 said yes, and 100 people in B where 20 said yes. And you'll see if I start, so there's a difference of 10% there. If I start making the difference larger, you'll see that the p-value goes down. Okay? And at this difference, where we had 17, the p-value is already significant, is smaller than 0.05. And the closer the results are to each other, the larger the p-value, meaning, see, now this is very large p-value. And you can get all the way. And here I'm just doing 100 permutations, but you can do more permutations, like you can do 1,000 permutations. You need to do a large enough number of permutations. 100 is probably too small. You want to do more like 1,000. Okay? Yeah, so you see, if I increase the difference between A and B, the p-value becomes smaller and smaller. Okay? Really small. To a point where it will become, it will run out to 0 there. Okay, yeah, now it runs to 0. Okay. So the more different the results are, the more likely they are due to a real difference between the options A and B. And the more close the results are to each other, like, here you have the same number of people in A and B, and 30 said yes in A and 25 said yes in B. That's very close. The probability of it being due to random chance is very large, as it's represented here by the orange, which is the p-value. Okay.
Carlos, did you just share the link to the notebook, or did you share the link to the packages?
I shared the link to the packages. We'll send the presentation afterwards by email. Okay. You'll get a zip folder with everything.
All right. Thank you, everybody, for sending me your email address, and we'll send the recording as well as the like Carlos mentioned, the zip file in the next few days.
Okay, I think we answered all the questions. If anyone has any last-minute questions. All right. Okay. Again, thank you, everyone. It was a pleasure.
Thank you, everyone.